With that, we'll jump into today's presentation, Understanding Pressure Transmitter Manifold Technology and Selection. Today's speaker is Liz Majestic. Liz Majestic is an application engineer here for Yokogawa. Liz works with pressure, multivariable, and temperature transmitter applications, and she works with customers and sales to identify, design, and verify pressure and temperature measurement applications for the best needs of each of our customers. We're thankful to have her here with us, and with that, we'll turn the time over to you, Liz.
Thank you, Josh. As Josh said, my name is Liz Majestic. Also with me is Lee Hamlet and Michael Keller. Michael Keller has been with the company for about 4 years and in this industry also. And then Lee's been with in the industry for about 12 years now. At any time, feel free to jump in, y'all, to clarify on the topic. Okay, with that, let's get started on understanding manifolds and technology and selection. We will go over a summary on the history of manifolds, the need for manifolds, different categories, industries that manifolds are popularly seen at, and a few key points on installation. Why is it important to look at the history? History helps us to understand change and how manifolds become popular in today's society. The original manifolds were a nightmare. They were hard to pipe, had multiple leak points, expensive to install and to maintain. So that began all in 1910 with the use of a differential recording gauge. It was a mercury type. It has 3 check valves. Let's see if I can point you. So in this picture on the right, there's 3 valves. It's in a U-type shape. These valves had problems. They had leak paths and had incorrect readings. So in the 1960s, so between 1910 and 1960s, customers and industries or manifold companies just basically were trying to improve that design. And so in 1960s, they actually came up with a 5-valve design, which we'll talk later in the PowerPoint about, but it had a different configuration to allow for the measurement not to be affected. Now in 1960, they also had the 3-valve, they fixed the 3-valve design, and it allowed for a rod-out feature. Now, a rod-out is a specifically designed rod that goes through the valve or opening to loosen deposits. The device is to allow the passageways to not be restricted. So that's something really wonderful when something's blocking, you can stick a rod in there to clean out. So that way you're not having to get a new manifold, and it's also not causing your process to leak. And then in 1963, 3 years later, the 5-valve came out with a new design, which is now considered the differential pressure manifold, which we'll also be talking about later on in the presentation. The main key feature, and it's on the right here, is it was used for compact saving, so saving space for your manifold industry, and that was really good. So now we'll jump into why you would want a manifold. So a lot of customers don't understand this, but they're actually making their transmitters work a lot harder when you don't have a manifold. You're causing yourself to have to pipe more than you need to, causing maybe more leak paths. It also allows, let's see, what is this? You're causing the transmitter to have to be pulled out of service, and the manifold allows you to keep it in service and just shut off that section for just a little bit, so you can do a quick on-site calibration or a zero check, so you can isolate the instrument from the process real fast. And also reduces the number of potential leak paths, and it saves you cost, which is wonderful. Who doesn't want to save costs on something? So, and also, it also standardizes on installations. So a lot of companies understand that they know what they need to, how they want to build their skid or how they want to put it out in the field, because the manifolds have been around so long now. And next we'll jump into different categories. Now there's 4 different categories I'll be talking about. There's classifications and And with classifications, there's two main categories, which are the connections of a manifold. So let me jump right in there. Okay, so these are the 6 main connections on the right. There's fixtures, and then there's the 4 bullet points on the left. But these are just the popular ones. You have your threaded connection right here, which is for your inline transmitters. It's usually an NBT by NBT. You can get other threads, but that's the most common one to get with that transmitter, or with that manifold. We'll also be talking about this specific manifold in the next few slides. So next we'll jump to the blank by blank. And the blank by blank is generally used with an equalizer valve, so you only have really one valve or, a mono valve. But it's also very popular in the 3-valve style, which I have shown right here, which it has 3 valves. And you can see that it's blank by blank because it's flat on both sides. Then we'll jump to the flange by flange. And the flange by flange, as you can see, it has a flange on either side, and it's also a 3-valve. You can also get it in a 5-valve or, 2-valve too. That's the picture I picked. The flange by flange close couples to the transmitter. That allows you to close couple to the orifice flange union. And then here is the pipe by pipe. It's also known as tubing by tubing. It just depends on what you've heard in the industry. It can be either one. It just depends on what you've heard. It's used for transmitters that have connections that are different than the standard 2 1/8 inch center. And we'll talk a little bit more about the pipe by flange, which is below. We'll just skip one. We'll go back. But this transmitter, or this manifold, is used with transmitters that do have that 2.8 inch center. Then we'll go to our final one, which is the most popular one, is the flange by pipe. It's used for direct coupling to the transmitter to the orifice flange. It allows you to rod out through the manifold and orifice tabs. Now remember that rod out feature, very important. Allows you to clean out your manifold. So now we'll move into our installed location. It's dependent on the application you have. It is also dependent on your primary element that is used. On the right here, we have the direct mount. Sorry, I didn't click properly. You have your direct mount. Now, your direct mount is great for your 3-valve manifolds. And in this picture, there is a 3-valve. I know it's kind of hard to see, but it's right there. This is your 3rd valve, and then you have your one here and one here. So it is a flat-valve manifold, or 3-valve manifold. So the good thing about this direct mount is it reduces your installation equipment, also labor and heat tracing costs, and your maintenance costs. And it's also good for simplifying on purging. It's the closest possible coupling to your orifice flange tap. Then we're going to move to our close coupled. Okay, now people think that direct mount and close coupling are about the same thing. The only difference between these two is that your direct mount is that your manifold is directly mounted to your primary element. This, with the closed coupling, your manifold is mounted to valves that then are mounted to orifice plate, your orifice plate or to your primary element. This closed coupling reduces pipeway space congestion and allows the transmitter to be more accessible for servicing. Then you have your line mount, and as you can see in this picture, let's see if I can get a highlighter. I'll do yellow. Let's see. You have these lines right here that go to your manifold and your transmitter and then go back to your orifice plate. The manifold is supported by the process line near the primary element, and that's what I just drew. So you see these lines are supporting the manifold and the transmitter, and it goes to your orifice plate. We'll go back to the pointer. And the most commonly one is, the two most common are the direct mount and the remote mount. The remote mount I see more often. And this one, it's used in a Varibar application. So you have a transmitter, a manifold, and then a Varibar application, or Varibar. So mainly customers use this manifold setup, or this insulation setup, for maintenance conveniency. The transmitter is generally mounted at a grade, but it allows you to get away from the process. So it allows your manifold and your transmitter to be away from any type of spillage, temperature, just so then your technician can get to your manifold and your transmitter easily, so then it can be easily serviced. So that's why it's extremely popular. It allows for your technician to get to it. So the next few slides, we're going to go over the type of instrument, and it's detailed on the slides coming up. Okay. So we're going to talk about the block and bleed. Now, as I said in a previous, it does have this threaded connection right here, this threaded manifold. So you have a block and bleed. Okay. So this manifold is generally used in gauge and absolute applications. The block valve isolates the instrument from the process. Now it is open, this blue isolation is open when it's in normal operation. But if you want to zero, like if you want to check for a zero, you want to check for calibrate, or you want to do a calibration check, for zeroing, you're going to block this blue valve, and you're going to bleed the pressure using the atmospheric valve, and you're going to have it fully vented. And then the instrument that you have up here should show a zero input. Now, if it doesn't, you're going to have to do some adjustments with your transmitter and your pressure to get it to go back to zero. But that's just how you're going to check for a zero. Now, for calibration, this would be generally done at the factory, but you can do it out in the field. That's the good thing about having a manifold. So the main important thing is to make sure that you have piping arrangements done, to make sure that, because you know it is a threaded connection, so you want to make sure that your threaded connections are right, because that can be a huge problem out in the field, especially if you order female and it's actually male or male versus female. The most common connection for this type of manifold is a 1/2" male to a 1/2" female. And this type of transmitter is an inline transmitter. So it's threaded directly to the manifold, and then this would be threaded to either your primary element or to a line. Next, we'll be going to another type of block and bleed, but it's a 2-valve. It's considered 2-valve. This is considered 2-valve also, but this is a different type of 2-valve because it's a threaded manifold, and this is for more of a traditional mount transmitter. And the manifold is a flange. As you can see, this manifold is a flange by pipe, which is what I was talking about earlier. This manifold you would be using in, again, absolute gauge, but you would also use it in high gauge applications. Traditionally, you're going to see it with a flange by flange or a flange by pipe, as I was talking about. You're going to have the same thing where you're going to block the process, bleed the instrument, you can still, and then you can show a zero. The block valve is closed, the bleed valve can be opened to vent the pressure from the transmitter. That way you don't have to vent it from the actual transmitter itself. So it's really good. And this one's just a flip. It just really depends. The atmospheric is here and the process is here. So it just really depends on the type of manifold that you get and the type of manifold company, depending on where this will be versus this. It just depends. So we'll go into the most favorite manifold, which is the 3-valve manifold. Now, the 3-valve manifold is going to be used in differential, high static differential, multivariable, and draft range applications. The 3-valve ensures a proper zero for the transmitter. It equalizes to prevent exposing low differential transmitters to prevent damaging gauge pressures during installation and removal. Now, in the next couple of slides, you're going to see a differential pressure 5-valve and a differential pressure natural gas. The natural gas is the same design as the 3-valve differential. no difference whatsoever. In Manifolds, it has 2 installations and 1 equalizers. Now, as I said, this is used for the 3-valve is used for instrument isolation, instrument zeroing, and it's also, you can also find it in liquid and vapor services. It allows the transmitter to be pressurized with line or vessel pressure before differential pressure is applied for flow measurement. Now, to check the zero, it's going to be a little bit different. You're going to close the downstream valve, open the equalizer valve, which is this green one. So your transmitter's here, and it's made it to your manifold. And then you're going to open, and then you're going to observe the zero and adjust if you need to. Then you're going to close this green little guy back up and open the downstream valve. And that's generally how you would figure out how to find the zero for your manifold, for your 3-valve. Now, you can also use this to check your span calibration. So what you're going to do is you're going to open both of these block valves. You're going to close both of these, not open. Close both of these block valves, open the manifold equalizer valve, which is, I didn't move it, it's right there. You're going to observe and then correct the zero. So you're basically going to start out and you're going to recheck the zero. Then you're going to replace the pressure from the instrument through the low side vent screw and observe the zero. So most of your transmitters are going to either have a vent screw on the side or on the back. So you're just going to open that up and you're going to observe the atmospheric pressure, or the zero at the atmospheric pressure. Now the good thing about this is anytime that if you see any type of unusual offset, that means that something might be wrong with your transmitter. So it kind of tells you something's wrong with your process, and you need to actually pull the transmitter from service and actually pull it from service. So if you see any unusual numbers, you might want to try to re-zero your transmitter and see if that works. And if not, there's more than likely something wrong with your instrument itself and not the manifold. So let's say that the instrument's fine, nothing's wrong. You're going to close the equalizer valve and keep the vent open still. And then you're going to check your input pressure. And you want to do a 10% to 100% of scale. Now you want to make sure the input pressure is accurately put. So when you want to make sure you're using an accurate machine and you're accurately applying exact pressure to your scale, to your unit. So if there's no minimum errors in the operating range, then you want to place your manifold and your transmitter back into service. And to do this, you're going to crack the upstream manifold valve slowly until the transmitter is back to line valve. So the end result should be that your valve should be fully open again. The vent plugs on both the high side and low side, so see this high side and this is the low side of your transmitter, need to crack to let all the gas expel. Then you want to securely put those back up, securely close them back up, and you're going to check for your output, again with a test meter, a test meter or a test gauge, and adjust the zero if you need to. And then now your instrument is back into service. Now we'll go to the next favorite manifold, which is the 5-valve. Okay. Now the 5-valve manifold has about the same thing as the 3-valve. Now, as I said, I did say that it looks like to be the same thing. You can use it in the same thing. But the only difference, the big difference, is that on this one, on the 3-valve, you were having to vent using the transmitter. On the 5-valve, you can vent using the manifold instead. So it's kind of good. It allows it so then you don't have to create any unnecessary leak paths or anything like that, and you can also separate it out. Now, you can use the 5-valve to do instrument isolation and zeroing, venting to closed system, instrument calibration, and it's also used in liquid and vapor services. Now, again, it ensures a proper zero for your transmitter, allowing you to prevent exposure, pressure to be equalized to prevent exposing low differential transmitters to potential damaging. So I'm basically repeating the same thing. Now, it has 2 vents, like I said, 2 vents, and then it has the green equalizer, and then it has 2 blue, or 2 valves that are isolations. And then you can see it up here in the manifold also. So you see your 2 blues on the right and left, and then your vents up top, and then your equalizers up in the middle right here. Now, that's just one type of manifold style. Sometimes it's completely different, you know, but you're always going to have that. On a differential 5 valve, you're going to have 1 equalizers, 2 vents, and 2 isolations. Now, like I said, it's about the same thing as the 3 valve. You're going to walk it through the same 0 and the same calibration, but you're just going to do a different step where instead of venting on the transmitter, you would vent on the manifold itself. So it allows you to do that. Now we're going to go into the natural gas 5 valve. It only shows picture. It doesn't show any words. So now the natural gas 5 valve manifold is ideal because of the double block and bleed configuration to ensure that the leak across the manifold equalizer line would not affect the measurement. Also, it enables depressurizing the meter and the calibration by introducing a positive signal on the high side or vacuum on the low side. Now, a 5 valve has 2 equalizers, 2 isolations, and 1 vent. See the difference between the differential, where it has 2 vents, 1 equalizers, and 2 isolations? The natural gas has 2 equalizers, 1 vent, and 2 isolations. So you can use this also for dual static pressure. It's also, people sometimes use it for separating. It's a good practice to separate alarm instruments from process variable measurement devices, where you can do it one on this side, one alarm on this side, one alarm on this side, and test it. So we're going to talk about zeroing and calibration. Now, it's different from the differential pressure 5 valve. For the 0, you're going to close the downstream manifold block valve. So this one and this one. Just say this is downstream. You're going to close this one, and you're going to close this one, this vent valve and this isolation. And you're going to open both of these equalizer valves up, this one, and check 0 and adjust if necessary. Now, to return to service, you're basically going to do the exact opposite of what you did, which is you're going to close both your equalizer valves and open your downstream block valve and vent the valve back up, and the vent valve back up. And now you've checked your 0 and you opened it back up. You did that in probably, 5 or 6 minutes instead of having to take it out of service. I mean, that's wonderful. Now, to check for calibration, you want to close both manifold block valves and vent valves. You're going to close all 3 of these right here. And then you're open the 2 equalizer valves, which then you want to, and it bleeds down the transmitter pressure by cracking the vent valve. So you're going to crack this vent valve back up. And then you're wanting to close the downstream equalizer valve. So now you have this cracked open, you have this one still open, and you have this one cracked. You have this one closed, and you have these 2 isolations closed. Then you're going to open the vent plug on the low side of the transmitter. So say that there's a transmitter here, you have a vent screw, and you're going to crack it. You're going to open it. And you're going to check, and you're going to make sure you apply an accurate pressure, which is 10%, 25, 50, 75, and 100% of scale. You're going to make sure that you can see that has minimal error. Now, if you need to adjust your transmitter, make sure you follow your transmitter's manufacturing procedure. Everyone's transmitter adjustments are different than the next company's. Now, to return this to service, you're going to make sure the manifold block valves and vent valves are closed, the two equalizers should be open, then open the valves at the measuring element, so your primary element. Then crack the downstream valve until the gas flow is capable of being heard. So you want to make sure that you're in a place where you can hear that gas flow. You don't want to be in a place where it's really, really noisy or you can't hear it, which I know it's really hard when you're, especially when you're at a factory or you're in a plant. Extremely hard to hear stuff. You want to at least be able to hear the gas flow. You're going to hold this open until you can't hear the gas flow anymore, and the result should be the valve should be completely open. So your downstream will be fully open after that. You're going to observe the zero on the transmitter and adjust if necessary. Then you're going to close the two equalizer valves and open the downstream manifold and vent valve, which your downstream manifold manifold would already be open, but your vent valve would not be, so you want to reopen that. Now your transmitter and manifold are back in service. So this is back in service and running again. You didn't have to take it out of, you didn't literally have to take your transmitter and manifold and pull it back and bring it back to the warehouse. You're already, you're doing it already in service. You're just taking it out for 10 to 15, maybe 20 minutes to check it. Okay, let's move on. That was the bulk of the PowerPoint. We're going to move on to our parts of the manifold, which are important to know the different parts of your manifold. So the main valve itself really is considered bonnet. You have a handle, then you have rolled steam threads, and then there's a bubble-tight shutoff, which is also called something else. It's called a spindle tip sometimes. Now your handle can also be allowed for anti-tamper. So, sometimes, technicians could be walking, they might hit a valve by accident. This allows you not to hit that valve, or just make sure that nobody touches the valve without permission. But in this case, this handle does not have the anti-tamper on it, and it's just a normal valve, or a normal handle. Then you have the rolled steam threads. The good thing about a rolled steam threads is it provides additional thread strength because the steam in the bonnet threads are rolled and not cut. So that's always good. Now, underneath the rolled threads is your packing. And I don't have that on there, but it is packing. And the two most common ones to use are Teflon or graphite, which I do have this, but it's for gasket. Then we'll talk about the spindle tip, which is also which is good for your bubble tight shutoff. Now, the original manifolds had issues with leak path, and the main problem was they didn't have a bubble tight shutoff, so it caused a lot of leak path. With this bubble tight shutoff, you're minimizing your leak path, and you're not having to worry about your valve leaking. Next, we're going to talk about the gasket. Now, gaskets generally go for the flange by pipe or the pipe by flange or flange by flange. You can use it, gaskets can be used in other connections too, but those are the most three commonly used. You would see a gasket. Teflon is common. It's very, 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 very common, but it has a limitation on temperature. Generally 450 to 500 degrees Fahrenheit is the temperature max on a Teflon. If you go anything over that, you're more than likely going to melt, or you're going to melt that Teflon. With this Teflon, you have to make sure that you correctly torque to make sure that you seal the transmitter to the manifold properly, because if you don't, you can cause a lot of stress on the Teflon, making it capable to be the manifold to leak. The one good thing about Teflon is it's easy to remove and replace. You're not having to fight it to get out. Generally, they just pop right in and pop right out, or they pop right out and they pop right back in. So that's the one good thing. A lot of customers love a Teflon gasket. Now, graphite or graphite, it really just depends on, sorry, I should have let you guys know. This is a Teflon gasket right here in this picture. And right below it is the graphite or graphite. Now this one is a graphite. Now graphite is a flexible form of graphite. It just really depends on the manifold company, whether they use graphite or graphite. Graphite is used in high temperature and vacuum environment pressure applications. They're generally seen in power applications also. They're used in refineries and cogeneration plants also. They seal greatly, but they're super brittle. I don't know if you guys can see this, but over here I pinched the graphole manifold a little, the graphole gasket a little too hard, and it actually broke it a little bit. So it shows that it's brittle. So it's very, very soft. So you want to make sure when you're putting this gasket in that you don't damage it at all, because you will see a leak. As far as taking them back out, they're kind of hard because it's kind of like glue. It's like just kind of hard to get right back out because it's compact and everything. So that's the only disadvantage of having the graphole, is you're going to have to fight it to get it out, and then you're going to have to, when you put the graphole back in, you just don't want to break it. Now, some manifold companies, what they do is they put a 3/16 foil insert around the graphole gasket, so then there's not that potential to have a leak, and it's just used to help seal the the gasket, the graphole gasket, to the actual manifold and transmitter. So it's really good. Now, as far as material, the customer has the most knowledge of their process. Therefore, they must make the decision on material compatibility. However, I did put the common most material picked for a manifold, which is the 316, the alloy 400, the alloy C276, duplex, super duplex, and you can also do Inconel, which Inconel is very useful in high temperature applications. It's become very popular nowadays. So that's all the special parts. There's more parts, but these are the top parts that you would want to know about for a manifold. So next we'll move into accessories that you can get with the manifold. Okay, so you can have a pressure and leak test done to your manifold. So the only bad thing is you have to have the transmitter attached to the manifold to do this test. There's generally two different tests that can be done. These are just two popular ones. There's other tests you can do, but this one's the hydrostatic test and the nitrogen test, and they're usually 1.5 maximum. So you test them to 1.5, the maximum working pressure of either the transmitter or the manifold. Most people go by the transmitter. That's just customer's preference. So, and what this does is it allows you to make sure that the manifold doesn't leak. So when it gets out into the field, you know for a fact that it's more than likely not going to leak, and you're good. Like, it's been tested, it should work in the field. So you're golden. Next, you can do a sour gas service on the manifold. This is available on manifolds because the bolting or other parts might come in contact with sour process fluid, which will cause stress cracking or stress corrosion. So this allows you to have your manifold to last longer in sour gas applications. You also have to meet the NACE requirement for this application also. So your manifold has to meet this application, or this NACE, for it to be considered sour gas. Okay, so you can also do power manifolds. Now, power manifolds are really common, but the thing with power manifolds is they go through a lot of testing to ensure that they meet this requirement of ANSI and ASME. The manifold must be designed to ANSI, which is for non-nuclear applications, and ASME for nuclear applications. So there's added features to allow the power manifold to be safer, which is like test ports that include built-in shutoff valves, and your atmospheric is plugged when not in use. Also, there's several codes for this manifold to pass, which are like material specifications, design of components, units, ratings, fabrication requirements, and testing and inspections. So the power, to be able to get a power accessory on your manifold, they go through a lot of service, a lot of requirements to be established as a power manifold. Then you have your oxygen clean service. This allows for your manifold to last longer in service, reduces the maintenance and replacement. So you would use this service in oxygen high contamination process environments. When they come out, they're generally in a bag, they've been labeled, they've been cleaned. Your technician will generally handle these in gloves, and your transmitters are also oxygen cleaned too. So you don't want to contaminate your manifold at all. So if it's been oxygen cleaned, a lot of technicians usually handle it with gloves, and they don't touch the manifold at all. So that's one key thing if you do get oxygen clean service. Now we'll go to industries that manifolds are popularly seen in. Let's see. You're going to probably see manifolds in the steel, the power, the chemical, the gas, the pulp and paper, and the code generation industry. Code generation, they usually use their biogas enters the manifold system, and it goes through like an iron sponge scrubber to remove harmful green gas, and the chiller unit to remove the moisture from the gas. So that's what happens when you do a manifold system for the code generation. Now for the steel, you have sometimes the manifold systems regulate the pressure and the flows of fuel, gas, and oxygen from the main supply to the cutting torches. And that's mainly found in the steel mill and the foundry applications. Most of these industries use them to improve layout with less hoses and connections. They also use them for increased energy efficiency with shorter flow paths, allowing for minimizing pressure drop and heat. So that's mainly what they use these manifolds for. There's also, so manifolds are really good for these industries. They're used quite frequently. Okay, so we're going to move into our last topic of this PowerPoint, best practice. So, installation. So here are some key points of installation. So when you're bolting your manifold to your transmitter, of course you're going to make sure you insert the bolts into the manifold to the transmitter. Then you're going to finger tighten the bolts, and then next you're going to do a cross pattern, which on this I have, and it has the arrows for you already, which it's not doing it. Hold on. Which you have here, then you have here, then you go up, and then you go down. Oh, sorry, that's not, didn't diagonal that one right. Okay, so why is it important to not torque all at once? Because you don't want to gall the threads. Another one is you want equal compression on the gaskets to create mating, to do a correct mating of the transmitter to the manifold. So bolting it is correct because you don't want to cause leak paths. You want to make sure that everything's right. So that's an important installation feature that you want to know. Also, make sure that you pick out the correct manifold to make sure it withstands the temperature and the pressure of the application. Most manifolds have a maximum working pressure of 6,000 psi. So when it comes to pressure on the manifold, you're good. Your limitation is generally on the transmitter. But that also can be, your manifold is also dependent on the material of the body and the packing that is picked when it comes to if it's good for that application that you're using it in. So, like I said, if you're going to use a manifold and you're going to put it in the sour gas application, you would want a sour gas service on it because you don't want it to go through corrosion a lot sooner than you need it to do. So, I know that I have brackets right here, and you would think that you would want to put it in the accessories, but it's really good for installation purposes because in 1978, someone thought about brackets for manifolds, and they became popular because it took the support point from the transmitter and put it on the manifold. The main reason that people use this was that piping could be done without the transmitter, and the transmitter could stay in the warehouse until it is needed. Another reason is for maintenance costs is reduced and allows the transmitter to be accessible. So you can do your skid, you can go ahead and do your skid, you can have your manifolds where you need it to be, Your transmitters are in the warehouse, you're good, you're set. You know, what happens if something comes wrong? Oh, I need to move this piping. So you're just moving a pipe in a manifold. You're not having to move a transmitter that could be bulky or anything like that, which most transmitters nowadays are not. But it allows you to finish your skid and then take out your transmitters and place them where they need to be, and you don't have to worry about, you know, oh no, I have to move 30 transmitters and manifolds. Scary. So rackets became very popular. And this ends my manifold presentation. Thank you. And if you have any questions, please let me know by using the chat thing on the WebEx.
That's right. Okay. Thank you, Liz. I appreciate your presentation. It was good, very interesting and informative. Again, like Liz said, we'd like to open this to question time. If you can use the lower right-hand corner of your screen, either the Q&A window or the chat window, we'll make sure to ask those questions and get them answered. Okay, we've got a couple questions coming in. The first one that I have is if we could go to slide 15 or page 15. It said that the manifold flange is by the length, and then you were saying that it was by the pipe, and they're asking what the difference is.
So the manifold is flanged by pipe. Is that what they're asking?
That's right. Flanged by pipe. Flanged by pipe versus flanged by blink.
Flanged by blank. Flanged by flange. So this manifold setup is flanged by pipe, and then you would also see it where it's flanged by flange. You could see a blank by blank, which is here we go. Sorry. On this slide right here, you can see a 2-valve blank by blank. It's just not very popular. Generally, you're going to see a flange by flange 2-valve or a flange by pipe 2-valve.
Okay, cool. All right, we've got another question coming in. It says, how long does it typically take for these videos to make it on the website, and can we get copies of the presentation? Absolutely. We're going to send the recording and the PowerPoint slides within the next couple of days. So probably by Thursday, you'll have them in your inbox. We've got another question. It says, is there a manifold solution for the coplanar transmitters? Coplanar transmitters?
Coplanar transmitters? Yes, you can do a bottom mount manifold. Yeah, coplanar. That's usually, you can do a bottom mount manifold. And it's just, basically if you were to take this blank by blank manifold and flip it down, that would basically be your bottom mount manifold. And it would go to it would go to a transmitter that has a bottom mount connection or a coplanar transmitter mount.
Okay, thanks. Another question coming in says, can the handles for the manifold be anti-tamper?
Yes, and let's see, hold on. We'll go to the bonnet. Yes, you can have this be anti-tamper. You can actually have a lock on your handle too to prevent people, where it's a key lock where you can allow people to they can't even touch it. They have to have a certain key to be able to touch that manifold. So you can have that done, be on the handle.
Okay, great. Here's another question. It says, on oxygen cleaned services, are the manifold and transmitter assembled and tested for shipment?
You can. They're handled with gloves. You can do that. They're just handled with gloves. It's just it's a different type of test. You would have to do a different type of test to ensure that you don't mess that oxygen clean up.
Okay, great. Here's another question. It says, what are the dominant failure modes you normally experience in these manifolds?
Can you repeat that question?
Yeah, it says, what are the dominant failure modes you normally experience in these manifolds?
Dominant failure mode. Lee, do you have a?
They leak.
Yeah, the dominant failures are they leak, and the leaks generally happen with the gaskets or the valves. The valves weren't correctly packaged right or had packaging right, and they caused a leak in the valve. And you can fix that by sometimes the two main things are tightening the handle, torquing it down more, or just tightening the handle more, and then changing out your gaskets, because you can, as I said, you can damage the gaskets if you don't torque or you don't mate it correctly to the transmitter.
Okay. Here's another question. It says, transmitter brackets are less expensive than manifold brackets. Can you use transmitter bracket when using a manifold, or do you have to use the manifold bracket and specify the transmitter less bracket?
No, you can use a transmitter bracket. I can understand that manifold brackets are expensive, but as I was saying in the installation, sometimes skid owners, or companies that are building skids, they want to go ahead and have their brackets on the manifolds already out in the field, and they want to keep their transmitters in the warehouse until they have to be brought out. But you can have a transmitter bracket and a manifold together and not have the bracket on the manifold. You just have to specify it on the transmitter and not the manifold bracket. Or, sorry, on the manifold.
Okay. Here's another question. It says, what is the difference between regular manifolds and power manifolds, and can you use them both for all applications?
Well, you generally use a power manifold in a power application because, ooh, my bad. My bad. I went backwards. Power manifolds have to meet this special requirement, so they go through intense testing, and you would use these for, power manifolds are used for, okay. So you would use, the power manifolds are generally seen in high temperature, because, I don't know if I also showed you, I did, graphite is generally used for a power manifold, and these are used for high pressured and high vacuum, or in vacuum pressured applications. So that is why you would want to use a power manifold instead of a regular manifold, because you can weaken your regular manifold over time, and you're going to have to replace your regular manifold more often than you're going to have to replace your power manifold. So that's a good thing of always making sure that you picked out the right manifold for your application, because you don't want to have to keep replacing manifolds over and over again, every year. If you can have a power manifold that, you don't have to replace whenever it just corrodes or anything like that, or breaks over time.
Great. Okay, here's another question for you. It is, what is generally supplied with a manifold in the box when you purchase a manifold?
Generally supplied in the manifold are your manifold, of course, yourself. The manifold, of course, you're going to have bolts, you're going to have gaskets, and sometimes you're going to have washers. And then you can also, if you got a bracket, you're going to see a bracket in there. If you got a material cert, you're going to see a material cert in there. Any type of certs that you want, you're going to see in the box also. So that's generally what you're going to see in your manifold box.
Okay, great. We've got another one. It says, when do you use a coplanar, I'm sorry, I know I'm butchering that, manifold, and versus when do you use a traditional manifold?
Okay, so you're going to use a coplanar manifold when you have a bottom mount transmitter. And I don't have a picture of that on my PowerPoint. Bottom mount manifolds, usually are used for, having the transmitter and the manifold in a one vertical installation, basically, where you have your manifold on bottom, which is mounted to the bottom of the transmitter. So think about this transmitter, this traditional mount transmitter, and say that you shorten the flanges and you flipped it. You flip these cover flanges downward, and then your manifold is going to be on the bottom. That's when you would want to use a coplanar manifold versus this you want to use a traditional mount manifold to attach to the thing. Now, you can put a bottom mount manifold on a traditional mount transmitter. Just sometimes they're mounted upside down, so that would cause you to have some space issues.
Okay. We've got another question, and I'm going to try and piece it together a little bit. I may need some help with this, Stephen. It says, in hydrocarbon service to the manifolds comply with ASME 31.3. I think they're asking if in hydrocarbon services do the manifolds comply with ASME 31.3. I think that's the question.
Well, for power manifolds, you would see the ASME V31, and then for your sour gas, which you would see for hydrocarbon, you would see the NACE, which is the National Association of Corrosion Engineers. We're going to have to look. We're going to have to look that one up to clarify, to make sure that that would meet the spec.
Okay, perfect, Steve. We'll give you a call and follow up with that one. Make sure you're taken care of. I'm not seeing many more questions come through. If you guys have more questions, please go ahead and put them into the chat box or the Q&A window. And again, we can ask those here, or we'll go ahead and finish it up. We'll just give a couple more minutes. All right, well, I'm not seeing many more come through. For the rest of you guys that are still on with us, if other questions do come up that you'd like to understand about transmitters or transmitter manifolds, please email them to us. We'd love to help you out with them. You can either email us at webinars@us.yokogawa.com or corporatemarketing@us.yokogawa.com or liz.majestic@us.yokogawa.com. And I'm sure Liz would be happy to help you with your specific application questions as well. Liz, thank you so much for your presentation. It was really informative, and we appreciate all of you guys joining us today.
Thank you, Josh, and thank you, everyone, for listening in and listening to me speak about manifolds. I hope everyone has a wonderful day. Thank you.
Thanks.